Okay, pre-filtering for anti-aliasing. I want to draw your attention to this pre-filtering word because it's easy to glom on the anti-aliasing. We're going to try to do some filtering to solve our problems in terms of the aliasing. Remember, the aliasing came from the sampling. So we're going to try to do something before filtering, before we do our sampling. So here's back to our problem. Here's our jaggies on our triangle. And here's our samples now drawn in 1D. And notice the problem. When I have a low frequency signal, my samples are fine. This is a pretty good representation. It's pretty close. But now when I get down to this high frequency signal, this is junk, right? Like these samples miss all the wiggles. They miss all the high frequency information that's happening in this high frequency. So somehow these samples, this sampling frequency is sufficient for this low frequency signal, but it's not sufficient for this high frequency signal, right? And the problem gets worse and worse the higher frequency I go. So now we come to a key idea. The key idea is we're going to try to get rid of these high frequencies first. Here's another picture showing the same thing. So here's a high frequency signal. Here's a bunch of low frequency signals. And when I try to do a reconstruction from this low frequency, from these samples, sorry, we sample this high frequency signal. We do a reconstruction from the samples, and we generate this low frequency signal, which was never here. That's an alias. So the technical meaning of the term alias is I had a high frequency signal, I didn't have enough samples, and when I reconstructed, I got a magic low frequency appearing. So if you think about those blinds from the office building, there was high frequency holes in the blinds, and then one of those blinds was acting as a sampling filter on the other blind, and we got this low frequency circular pattern. So it was the same kind of thing as this happening. The high frequencies end up in the low frequencies where they don't belong. That's an alias. Okay, so we need to filter out these high frequencies before we sample because they're causing us trouble when we sample. So now how are we going to do that? How are we going to get rid of these things? So we have this original spatial domain. We need to take our samples. So we need to do something in between to get rid of the high frequencies. Well, why don't we pre-filter? We are going to take this thing into the Fourier domain, cut off all the high frequencies, and then come back. And we saw that when we cut away the high frequencies, we get kind of like a blurring thing, right? So here's our blurry triangle. These are our blurry triangles. We'll talk about the Nyquist limit in a minute. We haven't said what that is. So here's our blurry triangle. Now we sample the blurry triangle. And these samples now are not full red or full right? They're kind of the in-between values that we got from our previous anti-aliasing that we talked about. But we now have a mathematical way to say why this is the right thing to do. We threw away the high frequencies and then sampled. So this was a pre-filter before the sampling. So how much pre-filtering do we need to avoid this aliasing? Okay, this is called the Nyquist theorem. So this theorem says you're going to get no aliasing if we sample sufficiently for the signal. So we have a frequency called the Nyquist frequency, and that's defined as half of the sampling frequency. So whatever is our highest frequency in terms of sines and cosines, we need twice that many samples. And then we'll be able to get rid of the aliasing. That's what the Nyquist theorem says. So it tells us how much to cut off. Yes, so to avoid undersampling, I see in the chat. So to avoid undersampling, you take more samples. Yeah, so this doesn't seem like rocket science. Yeah, but I'm leaving out a lot of details so far about infinite extent, and we're gonna come to those. So here's a signal. Here's a sine wave signal. So our max frequencies are here. So our Nyquist, this tells us how many samples we need, right? So if we could go get the frequency of this, it's 1/32, right? It's here, so I'm gonna have to sample at twice that. Basically means I need samples on the white and black lines, right? Like I can't miss, is what it means. So I've tried to produce slides that make it relatively intuitive. So I'm super happy by people saying it doesn't seem like rocket science. That's great. I'm trying. So audio is at 44 kilohertz. So I see in the chat somebody mentioning that. So then what's the maximum frequency we can represent in the audio signal? So 22 kilohertz, right? 22, right? Because of the Nyquist limit. So if you had higher frequency harmonics or signal in your audio signal, your CD is going to chop it off, or your MP3 sampled at 44 is going to chop it off. So when we went from records to CDs, which I understand is well before all of your time, there was a lot of angst over this. People bought analog stereo systems and still do because they feel like they can hear those things above 22 kilohertz in the audio signal, and they get chopped off when we go to digital, and people don't like it. So yeah, I don't know if I can hear it, but I'm not an audio person. People believe that they can hear it, and so they buy high-end equipment to get it. Right? Why was 44 kilohertz chosen? Because it's sort of about the limit where most people are not going to complain. So in the audio world, right, this is a choice that was made because of this Nyquist frequency limit. Okay, so now where is the real challenge? Okay, here's our real triangle. This is a hard edge. If I draw this thing in 2D, this is a square wave, right? So now, how many sine waves do I need to represent this square wave, right? Meaning this edge in our triangle. To get this perfect, I need an infinite sequence of sines and cosines. When I take the frequency transform of a hard edge, I end up with infinite frequencies going out. Now that's going to cause us some problems because we can't get it perfect. No amount of super sampling is going to be enough, right? I have infinite frequencies, I need infinite samples. Okay,